Actually, don't know if we'll get that far. Good, hopefully we will. Hey! All right, well, welcome back, and let's keep working on our optics. Unfortunately, I've been a little too talkative with all this, and there's just a lot of stuff to do. And so with that said, I'm hoping now, finally, let's get done with the chapter 36. We touched on the lenses. We probably need to put a final touch and show you kind of the connection between the lenses and the mirrors. My approach, I think, as you caught, was to spend a long time on the mirrors with the idea that the lenses would fall into place on their own, and that may or may not happen. So I thought, okay, maybe one more hour might be good with the lenses, and then we better get on into the other part of our optics. And optics is kind of broken down into two halves, and this chapter 35 and 36 is the first half, and I'll show you what's coming here in 37 and 38. But basically, we are looking at our optics in terms of waves coming up. We haven't really treated our light as waves yet. We just have treated them as rays, and that's all we've done so far. So, putting on the board what we've learned is over here on the side, here's the big picture. That 1 over P plus 1 over Q equals 1 over F. And when we got started many days ago here, I was trying to convince you that this equation is the mathematical equation that connects object distance, image distance, and the focal length. And it works for both the mirrors and the lenses. And so we quickly did this right away for the mirror. We did realize that it would only be valid excuse me, if we paid attention to a sign convention. And so let's not repeat all that sign convention, but you remember all those sign conventions, and we came up with the idea that the focal length would be half the radius of curvature for the mirrors. And so we did a number of examples that way. We also talked about the magnification, which said that it would be the ratio of the height of the image to the height of the object, which turns out to be the same as the ratio of the image distance to object distance, with a negative sign in there. In fact, this week's lab, I think you will find very educational, maybe even a little long. So I guess I would encourage you to look at your lenses ahead of time and don't come in there just an empty slate. Or if you do, I guess maybe the good thing is you will learn a lot. It will take you a long time to learn a lot, but there is 5 lens problems. The first 2 are single lens, but the last 3 are double lens systems, where you again form an image from the first lens, and that image of the first becomes the object of the second, and all those good things that we talked about and will demonstrate here today. But as we got into the lens, we said this equation would still work. Now, there were some qualifiers there, if you remember, and we came up with this. We came up that with 1 over P plus 1 over Q still works so long as you take the definition of the focal length for a lens to be a bit more involved than it was for the mirror. The mirror was just half the length of curvature. And we argued that the bending of light would occur both when the light was going into the lens and when it was coming out of the lens. And just to throw some qualifiers in there, these ones up here, if you remember, came from the refraction of an image, or the image formed by refraction when we did it twice. And so that was index 1 over object distance, index 2 over image distance equals number 2 minus number 1 over the radius. And so this was the equation we had where an image was formed by a single refraction. But when we built a lens, it was a double refraction. And that is, it went in first. I shouldn't use double refraction. That's kind of saved for a different meaning, which we won't get to in this semester. But it's a refraction that occurs when it's going into the lens, and a refraction when it's occurring out of the lens. The two together is the totality of the lens. And so if you're willing to call this then the focal length of it, then it fits this same equation that we had for the mirror, and that's kind of nice. That's what I was getting at, that we can have the same equation applied to the mirrors and to the lenses. Of course, like I said, the lens being a bit more complicated. So let's kind of finish here up by looking at the lenses in more detail and hopefully connecting it back to how this is just like the mirrors. And so hopefully then everything we said about the mirrors, I won't have to say again for the lenses. You can apply by analogy what we had done for the mirrors to the lenses. That's my hope anyways here. And so I want to get started here by looking at perhaps a lens. I think it's in this box. Nope. That looks like, say, this. In other words, the light, and I'll put the laser beams up here, but the light's going to come in and it's going to hit a curved surface, then go through and hit a flat surface. Your author does this one first. That's not it, but image, I think it's figure 23 behind here, right here. He says, look at this for a moment. Here comes the light. It comes in parallel, hits a curved surface, and then a flat surface. So since it's curved out, it's convex. Since it's flat, it's a plane. So we call this a plano-convex lens. All right? But if you take a look at the equation here, as the light comes in, would the radius of this first curvature be a positive number or a negative number? For the lens, when did we call R positive? All right. So, the sign convention is crucial here, okay? But here's our sign convention. It works both for the mirrors and the lenses if you say it this way. The R is positive if it's on the side, that is the curvature, the center of curvature, is on the side where the light goes. So if it's a mirror, light comes in, reflects off, concave, that's a positive R. If it's a lens, then if it's curved this way, the light goes on that side, right? That's where the light goes, and so R is positive on that side. So again, what could be a little bit hard for the mirror and for the lens is they are on opposite sides when you draw a diagram. But the thing for me to remember is it's positive when the light goes there. Same thing with the Q. The Q is positive where the light goes. So again, if we have a mirror and the light hits it and bounces off, this side over here is where the Q is positive. If it's a lens or a refracting surface, the light goes through over to this side. This is where Q is positive. So the Q is positive over here for the lenses. It is positive on this side for the mirrors. The way to put those together is to say the Q and the R are both positive when it's on the side that the light really goes. Now, with that said, this laser beam are going to come shining in. It's going to hit this surface, and the light's going to go through to this side. The curvature is on this side. So I ask again, is R positive or is R negative? Yeah, it is positive. And that was our definition of a positive R. So this is positive. R2 is kind of a wasted question. Is it positive or negative? Because what is its numerical value? Infinity. And so 1 over infinity, whether we want to call it positive or negative, is still 0. And so when I look at this, I would say, in this case, I have F greater than 0. Now, hopefully this looks a little bit like the concave. The concave mirror, and so I'll put lens, but the concave mirror also had F positive. And so hopefully I convince you in this last part of the lecture that the concave lens behaves like, the convex lens here behaves like the concave mirror. They each have a positive focal length. They each have the same behavior. If I turn on my laser beam and even go back to the concave mirror, you will remember, I trust, that the concave mirror made the light converge. And so there's the converging of the light. Take away the mirror, what does this lens do? It makes it converge. Exactly. And so it curves in and makes it converge. And so what we have is we have what we would call then a focal point. And it would have a given length called its focal length. And that's what the author is trying to show here in figure 23, that light coming in really would focus to a point. It is a real focal point. We label it as positive. It's like the concave mirror. So the convex lens is like the concave mirror. That's the point. And so everything we said, everything we did with the concave mirror, that includes, remember those three options? What could the concave mirror do? And also, as we'll see for the convex lens, it can make it upside down smaller, it can make it upside down bigger, it can make it right side up bigger. And we'll see exactly that same idea here. All right, here's a fun question. What if I reverse the lens? And so instead of first hitting the curve and then the plane, what if the light comes from the other direction and hits the plane and then the curve? Does it still come out to be a positive focal length? Does it still make the light converge? Is the distance of the converging lengths the same? Well, what you're really saying here is look at this equation. If you turn it around, R1 becomes R2, doesn't it? Because instead of hitting the second surface, now that becomes the first surface. Fair enough? And R2 now becomes R1, doesn't it? But it's even better than that. Isn't it in the opposite direction? Because if I turn this around this direction like that, that first surface, R1, is now over here. It's R2, right? And the center of curvature is on this side, which is labeled as a negative. So look closely at this equation. What if I were to take this equation and replace R1 with negative R2? And I were to take R2 and replace it with negative R1. What do I get? Same thing. So do I still have a positive focal length? Mm-hmm. Is it the same numerical value? Mm-hmm. And it doesn't change. And that's what the author is trying to illustrate here, that if you send light in the other direction, it is still going to have a focal length. I mean, if you want to call them 1 and 2, that's fine. I like just to say there's 1 on both sides. He's trying to illustrate that they would be the same numerical value. And so that is a little different than the mirror. Remember, the mirror, we only had how many focal points? 1, right? Or did we only have 1? Didn't the light come in and go by the focal point, hit the mirror and bounce off and go by that same focal point? So granted, it was only 1 focal point, agreed. But it went by it once and then reflected off and went by it again. Don't you see that in the lens too? Isn't that what's going to happen in the lens? If I have a lens, the light comes in and goes by 1 focal point, goes through the lens and goes by the second one. And so again, they're exactly the same. A little different because one is a reflection and one is a refraction. But if I turn down the lights here and take this lens and turn it around, you will see it doesn't matter whether I hit the curved surface first or the flat surface first. Huh?
Which lens is that? Is that A or B?
This is A. This is A. It's curved this way. Yeah. And it brings it to a focus point. I'll turn the lights back on so you can kind of see it. I know this has got notches on the top, but ignore the notches. Right? See, there's the curve. Right? I could extend this a little bit further, and you might recognize what would happen if I had something that looked more like this. And so both sides are convex. Instead of just a convex plane, I have a double convex lens, is what we would call this. What would happen here? Well, let's see. Would R1 be positive or negative? Positive. Would R2 be positive or negative? Negative. But there's a negative there. So negative and a negative make that positive. So that's positive and the whole thing's positive. And so both of these surfaces make it converge. And so I have a lens like this. I get a focal point that kind of makes sense. It's much, much smaller in distance because both surfaces are bending the light down instead of just one of them. Okay? But it's still a positive focal length. And if I switch it around, this one probably without question ends up being the same focal point. And so, but even if they didn't have the same curvature, as you hopefully can see in this math, they would have the same focal point. So things that are convex then have a positive focal length. How would you get a negative number up here? And what would a negative mean? Look at this shape, a concave shape. I'll take this out here for a moment and grab, I guess this one here. And again, ignore the notches up there, but I'm hoping you can see this looks a lot like a concave and a plane. And if I were to come over to here and put it in this equation, I would look at this as R1 positive or negative? Negative. And R2 would have what value? I'm not even going to worry about positive or negative. Infinity. And so I would get a negative focal length. And so something that looks like this then would have a focal length less than 0. And if you remember the mirror that we had, the convex mirror had a negative focal length and made the light diverge. And so this lens, hopefully you will see, is just like this mirror. And if you recall, this mirror made things right side up and smaller, and that's exactly what this one does. If I place it in here and power down the lights again, you will see that it makes the light spread out. And in this case, it kind of looks like the light is coming from right there. And so that's the focal length. It's a virtual focal length. And so as this is trying to show in the picture, the light comes in and spreads out. There is your focal length. And whatever number you got, which was negative, we can do the same argument that if you switch the lens around, or in this case, they switch the direction that the light is coming, you are going to still get a focal length that is negative. And exactly the same numerical value, because again, what you would be doing mathematically is you would be replacing R1 with negative R2 and R2 with negative R1, and as I tried to show, whether it is a positive focal length or a negative focal length, you're going to get the same numerical value. And so just like the mirrors, we have our lenses. This is our convex lens, and it does everything the concave mirror did. This is our concave lens, and it does the same thing that our convex mirror did. The only difference then between working with the mirror and the lens is that we need to realize that the focal length is calculated differently, and because the cause is different. The cause of the focal length for the mirror is reflection, and the cause of the focal length from the lens is because of the refraction, and then twice. But we can still use this, and we can still use this. This would give me that. And so your author says, let's look at some other lenses that we might build here. And so coming back to our pictures here, let's go to figure 25 here. I've shown you this one, the plano-convex and the double convex. But this one too would come out to be positive. All three of these are positive. Hopefully these two are obvious why they are positive. This one's, I don't think, quite so obvious that it is positive because it's got two radii of curvature, but they're not the same numerical value. They are both positive. And so when you look at that, you will see here that R1 and R2 are both positive numbers. However, you will hopefully notice that the second radius of curvature is a bigger number, if you will. In other words, the front edge is curved more. So if you take 1 over a small number, that is numerically bigger than 1 over a big number. And so yes, you have positive, and then you have negative another positive, but this positive is bigger than that positive, and so the whole thing comes out to be positive. And so this is a positive focal length, although it takes a little more thought to kind of come up with that. Yeah.
Did you say the radius for the second one is both positive?
For the second one, they're both positive, right? If light's coming this way. Okay, if light's coming this way, then they're both negative. But then, if I think of it that way, these are both negative, fair enough. But the one it hits first is a bigger number than that one. So the negative with that negative make this a bigger positive number than that is negative, and you still come up with a positive. And there, that's our mapping, if you will. So you're still going to come up with a positive number regardless of which way the light goes. It's just the sign convention would be a little bit different, but then so would the order of what you call R1 and R2. And so you still come up with a positive. Most of the lenses we will work with are like this. I mean, why not? You're trying to make the light converge. You might as well curve it both ways if you're trying to get the light to converge. So that's why you will see in the lens and the equipment you do this week, you will do a lot of that. You'll take a double convex lens. But of course, it's worth mentioning and pointing out that that's not the only one. Here would be a positive. And I don't have any type in my optics box that has that second shape, except that second shape, as you can see, might be useful for a pair of glasses on somebody's face, because when you put it on somebody's face, you're trying to keep it the curvature of their face there. And so reading glasses do exactly that. If I were to put, I stole these from Don, so I've got Don's reading glasses up here. But I'm hoping you can see the light comes in and it converges into a, not quite a point, but maybe if I moved it a little bit further, but there is the curvature to them. I don't know if I can even see them with the laser beam. It might be worth trying here. Yeah. It's got to be closer to the board there. But I know I can see it with the light from the overhead. It comes in and brings it in. And so that, of course, is magnifying things. Because didn't we say, what was the nice thing about the concave mirror? What did it do? It had three options, but one of them was to magnify. And magnify and keep it upright, which would be very useful for a pair of reading glasses. Magnify it and keep it upright. And so there is our conversion. Whereas these other shapes all have a negative focal length. So they all fit the same thing we did with the convex, which always makes things smaller and right side up. Oh, yeah, I might want to try those. Here. But this is the same idea. You got both on there then?
Yeah.
Oh, some bifocals.
Yeah.
Sweet. See what happens here. Hopefully it's not too complex that it fouls things up. But makes them harder to understand. But you saw these already, how it makes the light diverge. And again, the ones we use in lab are going to look a lot like this. Why not? Make it a double concave and, bend the light out. But if you're putting it on somebody's face, somebody who's nearsighted, this would make the more sensible thing to do, because it would match the curvature of their face. And so this is for somebody who's nearsighted. And before I use yours, David, I will do mine. I'm nearsighted, and so mine is curved. And if you look closely, you will see this curvature has a smaller radius than that one. And so it's just the opposite of that. And so light coming in would hit this one and this one. Coming this direction, I would call the R both positive numbers. But this first radius would be a bigger radius than the second one. And so 1 over a big number comparing to 1 over a small number, 1 over a small number is larger than 1 over a big number. And so that negative piece is bigger than that positive piece, and you end up with a negative focal length, and the light would diverge here. And so my glasses are like that. Not too much curvature to them, but if I hold them up here, I'm hoping you can kind of see how the light on the glasses opened up and it spread it out, making where it went through the glass a little dimmer, but making it bright there on the outside. And yours, you got both, right? I don't see any nearsighted. I see.
No, far-sighted.
Oh, you're just farsighted. Okay. So yeah, so you're the farsighted, and then down below it you've got reading glasses on. Yeah. So you've got both are converging, and then one is more converging than the other.
Reading glasses are closer to the edge and might work with the laser.
Oh, I get you. And so, since it's close to the edge, yeah, kind of see it. But we better move on. We got lots to do. But anyways, you see the idea. Let me give your glasses back to you. But converging or diverging, which most of people who wear glasses are nearsighted. So I suspect most of you, if you have glasses, have this kind of effect. And if you put them out in the sunlight, you would do this, and it would spread out here, and you would see that light spread out. Which is also why, remember this lens, the negative lens, which again matches the convex mirror. What do we say about the convex mirror? What does it make things look? Smaller. Now, don't get me wrong, with your eyes, that's just a corrected vision, but what does that mean for somebody looking into your eyes? Don't they have to look through your glasses? So how do they perceive your eyes? Smaller, right. And so that's why, without your glasses off, besides the frame, you can look different because your eyes are bigger, which usually people associate with friendly. That's why nearsighted people are these angry-looking people, with these squeedy eyes, because the light's got to come through there and makes us look like we're out to get you. Well, we are, but that's beside the point. But that's what happens with the nearsighted people there. Well, let me keep going because I kind of want to do a couple ray tracing, but we need to kind of move into the next chapter here. But picture 27 is worth showing before we go too far. If I were to look at this lens, I guess I'd call it a plano convex, right? Would it be a positive or a negative lens? Positive, right? Okay. But remember, the bending occurs only on the surface. So Fresnel had a great idea. Oh, why make a big lens that is mostly glass that's not needed? What if you took the edges, you cut them off, and you glued them all together? Wouldn't you kind of get that same effect? Here is his approach. Why make a big, thick lens? Why not just kind of put it, bummer. Put it, there we go, on something that is thin, flexible. And so I can take a piece of glass, cut the ridges on it thin enough here, and hopefully then as I look through here, I will then have the effect of a lens and a positive lens. And of course, what did we say about a positive lens, which is the same thing we said about a positive concave mirror, is that what happens when something is close to it? Right, it made it bigger and right side up. And I think that's what you see in terms of my face. You see my face close, and it is bigger and right side up. Whereas me, when I look at you, you guys are far away. And so what does the image look like for something that is far away? Do you remember the image far away? What did it do? Turned it upside down and smaller. And so as I look, I see the whole classroom inverted. Here's just the opposite. Here would be a negative lens. In fact, this is so negative that I don't know if you can even see. Can you see the light right here? Yeah. And so it hits and it really spreads out. And so, yep. As long as it's off, we'll take it off all the way. But here is the flexible lens. And if I were to look through this, I would hopefully see things that are smaller. And I do. I see the whole class. You're right side up, you're smaller. And of course the real advantage of this, as we talked about before, was the wide angle viewing of it. And so this is one of those ones you see glued on the back of those RVs as they drive down the road there. I'll toss these around here if you want so we can kind of finish up here. But those are our two type of lenses. So if I were trying to draw some rays, let's draw a couple of these. Unfortunately, with time, I'm not going to be able to draw all of them, but I'm hoping I don't need to. I'm hoping what can happen here is everything we did for the concave mirror, you will recognize the same for the convex lens. And everything I did for the convex lens, you will recognize for the convex mirror, you will recognize as the same as the convex lens. So maybe I should start with one here. Let's do this. Let's remind ourselves of the concave mirror. Let's put a focal length and twice focal length, which was center of curvature. Let's put an object out here and let's draw the rays. Didn't we say the first ray would come in, hit the mirror, bounce off, go through the focal point? Then we said the second ray would go through the focal point, hit the mirror, bounce, and go straight off. And if we put a dotted line down the center, then those two would meet here, and what we would get is we would get an inverted real image that has a magnification that is in magnitude less than 1, but in sign is less than 0. And so that was our concave mirror. So let's look then at a convex lens. We would have a focal point. But as I was trying to show you a few moments ago, we would have a focal point on the other side. And so again, seeing the analogy here could be a little tough because how many focal points did we have for the mirror? Well, just one, kind of, but didn't it come in, go by the focal point, bounce off the mirror, and go by the focal point a second time? And that's exactly what's going to happen here. We don't have a reflection, but if I do have an object out here, what would happen to the first beam that comes in and hits the lens? It bends and goes through that focal point. Now I'll keep my drawing a little bit simple. Doesn't the light bend when it goes into the glass and then bend again when it comes out of the glass? So the real bending occurs twice. But just to keep my picture a little bit simple, and I would encourage you to do that in the lab when you draw your ray diagram in the lab tomorrow. But we'll bend it just one time, right in the center of the lens. Okay? What about the second ray? And so the second ray hits the focal length first. And again, I'm hoping you see by analogy, isn't that what I did up here? Right? I drew it parallel, and then after hitting the mirror, it goes through the focal point, and then the other ray was to go through the focal point first before it hits the mirror. And that's exactly what I'm doing there. So again, wish we had more time, but we really need to move on into the other stuff of here, otherwise we're going to miss out on some neat stuff on, well, coming up here. But we need to then draw the rays here, and you will hopefully see that there's my image. And so again, same thing. My image is inverted. Its magnification is less than 1, or at least the magnitude of the magnification is less than 1. And of course its sign is negative. It's inverted. What would happen if I changed all this? And let's see, I guess I want to leave those equations there. What would happen if I took and had the object a little bit closer to it? Maybe I'll do the mirror first again. Maybe I'll put the focal point here. Maybe I'll draw the object right there. Do you remember drawing that one? Do you remember what you got?
Upside down and bigger.
If I'm in the focal point, it's right side up, virtual, and bigger. I kind of skipped the one in between there. So I went from all the way outside, since these are kind of the reverse of them in interest of time. Let me just go all the way in. And so this ray would bounce off and go through the focal point. This one coming up from the focal point would bounce off and go parallel. These two would appear to be coming from right there. And so my image would be magnified, if you will, greater than 1, but not inverted. And so what do you think would happen if I took a convex lens? And I put a focal point, and I'll put a focal point on both sides. And so that's kind of what would be different in my drawing. But if I put an object that is kind of close to it, what would happen to the beam that went parallel? Right, it would bounce, or excuse me, not bounce, it would refract and go through the focal point. Just like this other one was the hard one to draw, this one can be a little bit harder to draw, especially in my drawing, because the one coming from the focal point doesn't actually hit the lens. I haven't drawn the lens big enough. But remember, this is just a drawing, so this ray may not actually go through the lens, but all these other ones will do it. So I might as well just draw that one so I know where the other ones would come from. But this one would end up going parallel. And so as you trace this back, you would get something that looks like that. You would get, again, a virtual image. Somebody standing over here would be looking back and saying, there is what it looks like. There is the image. And that image then is bigger than the object, and it's further away. And we can do all the same calculations that we did for the mirrors we can do for the lenses. And that would be my drawing, if you will, of my convex lens. Maybe I'll show you one more, and then we'll do a couple of problems, and we'll see how you do on the homework. But let's draw the other lens, which is the concave lens. And as I was trying to point out, that concave lens is the same as the convex mirror. So let's draw the convex mirror first. So here's the mirror. It is a convex mirror, which meant it had a negative focal point and a center of curvature, which was twice that distance. And if you recall from a couple of lectures ago, if you took an object out here and you drew a ray that was parallel, it would bounce off as if it was coming from that focal point. That's why we called it a virtual or a negative focal length. The second one to draw was a little bit harder. It was the one that was going towards the focal point. Of course, it doesn't actually get there because it's a virtual focal point, but it bounces off and goes parallel. And so somebody standing over here looking at these two rays, this one and this one, have the appearance of coming from right there. And so this is the one that always gave us a right side up and smaller image. Yeah.
Is this a positive or a negative radius? Which one is positive radius?
This is the mirror. Okay. And it's positive or negative whether or not the light went to that side. So, light hits here, bounce off. Did light go to this side? No. So it is negative. So this is negative for the mirror. Don't confuse it with the lens. So let me draw a lens. Here, I will then draw a concave lens. And the concave lens, again, would have a focal point and a focal point. They're negative focal points when we do our calculation because, again, as the light starts from, say, over here and hits this surface and goes through the lens, where's the center of curvature of this one? On this side. It's on the side where the light doesn't go. So it's a negative radius of curvature. So for the mirror, this is a negative radius of curvature. For the lens, this is a negative radius of curvature. It's negative where the light doesn't go. It's positive where the light does go. Okay. So keeping that in mind, if I were to draw a ray that is parallel like I did here, what would it do? Yeah. Diverge out as if it is coming from that focal point. That's what we meant by the diverging mirror or the diverging lens. Both of those spread out as if it was coming from that virtual focal length. And again, the second one is kind of a hard one to draw, just like it was here, back up in the mirror. You'll see we were drawing it towards this focal point. I'll do the same thing. What would happen to a ray that I would draw heading towards that focal point? And then so notice I'm using both focal points. Just like you might say I use both focal points for the mirror. But the mirror doesn't really have two. But what it does have is it has a reflection. So one coming in and one coming out. The lens doesn't have a reflection, but then it has the two, one on each side. And so if I draw a ray that is coming towards that focal point, it would bend out and go straight. Exactly. And so again, mostly because we're slow on time, can you see the analogy? You see how if we know this one, we also know this one? Everything that this one did, this one does. Same thing here. And so take all that wonderful stuff we did for the mirrors and extend it to the lenses. What would somebody standing over here perceive? Now this ray would be coming back from here. This ray would be coming back from there, they would meet right there, and so somebody would perceive something that is smaller. Right side up and smaller, which again, same as we got there. And that's what I wanted to show you. And unfortunately, about all the time we have, although I kind of want to point out a few other interesting things, and I wish we had more time. But as you go through the reading there, you will come across, of course, many of the applications here. One of those is obviously very clear for a lens. Your author does a good job in picture number 33 here and say, where would I use a lens, whether it be a converging lens or a diverging lens. Here is a converging lens. You can see the double convex lens in the camera. This person is trying to take a photograph. But how does the camera work? Or at least the optical part of the camera. Relatively simple. There is something you're trying to take a picture of. You are a certain distance away. That's P. That is the distance to the person. You want to then form an image, a real image, so the light really goes there. So a virtual image will not work. That's why this lens, like this mirror, is not going to work here. You want to actually get it on the screen. You want the electronics to get the energy from the light. You have to have a real image for that to occur. You go to the movie theaters and you look on the screen. What kind of image is that on the screen? Real. Why? The light is really there. It's not just perceived as the light reflecting off of there. The light has been projected onto that screen. There's really light on that screen, and then it's bouncing off and coming to your eyes. And the same thing with the camera, the CCD array that is back here. We want the light to really hit our electronics. Or if you're old school, we want it to hit the film and make the photochemical reaction here. But we got to get that energy there. So the idea is to form a real image, which only can occur with the converging lens. And that would be my Q. And so this is P, this is Q, and those have to match this mathematical equation here. When it comes to the lens that is in my camera, the R1 and the R2 and the N are already determined. So simply put, I have a fixed focal length. The focal length is fixed. I can't change that in my camera. But what I can do is adjust the position of the lens. And as I rotate, or as I let the electronics move the lens, this lens can move in and out, changing Q and changing P, such that the product, or the equation, is valid, so that 1 over P plus 1 over Q equals 1 over F. And that means basically if I was taking a picture of something really far away, 1 over P would be almost 0. So my Q, my image distance, would be basically just the focal length of the lens. But as it gets closer and closer and closer and closer and closer, 1 over P becomes a significant number. Therefore, 1 over Q needs to become smaller, which means Q has to become bigger. And so as I use my camera, and as objects get closer, I start adjusting it so that the lens keeps moving out. And obviously the lens can only go so far, and then that's why I can't focus on anything closer than a certain distance. And so depending on your lens and your camera, you can have a near point, and I'll just say 1 meter, that, look, you can focus up to things 1 meter. If they're closer than a meter, you need to change, and many of the cameras have a close view lens, and you put a different lens on there, or you add a different lens to your optics and do some other things there. But just the simple idea of the camera, I can only get so close. Which is an extension then of what I wanted to say. What might be another nice optical element is that thing. Believe it or not, that's supposed to be a human eyeball there, but here comes the light. It comes in and it hits the cornea. The light bends. It goes into the eye and it hits a lens, and it bends yet a second time. And so kind of a simple picture of that is this. the light comes in and it bends on the cornea there. We talked about this before. If you're underwater, what's going to happen? Doesn't bend nearly as much. Now, your eyes try to adjust underwater because they can take the lens and this little muscle here and kind of squish it down. But what's different about the eye compared to the lens is that we can change the focal length of the lens. What we can't change is image distance. We don't move the lens in and out. And so this distance from here to our retina here is the idea of we want to get that in focus. And so our Q becomes a fixed number. But other than that, it's simply the same basic physics that, look, we want this to be the set number. So if we were to look at something really far away, and if you look at something really far away, then you can kind of ignore 1 over a big number, and so the image distance is the focal length. And if your eyes are designed and work correctly, that's usually what happens. You look at something far away, your muscles relax, this is flat, and the focal length from your cornea is just enough to get it right there, and you get a perfect image formed. If you're nearsighted like me, that doesn't work, unfortunately. This is curved too much. And what ends up happening is when you look at something far away with no glasses on, it curves too much and the image is formed right there. So by the time it gets to your optical nerve, it's a blurry mess. And so you can see things close up because you've got too much curve to it, but you can't see things far away. You can get laser surgery and they can change the curvature here, and so then you don't have to, that same problem, but that's the eye, yeah.
So like having glasses is inherent?
It's what?
Like when you have glasses, is genetically, you just need glasses because of your genetics?
Well, yeah, this is not built right, and there's a number of reasons, but genetics is a big one, yeah. But it also can be the pressure on your eyes. I mean, look what happens when something's close. Again, just like the camera, if you get closer and closer and closer and you're looking at something like reading a book instead of looking off into the distance, what's going to happen then, if we come back to this equation, is you have a 1 over p, and now that's not 0 anymore. This you can't change, so what ends up happening is you want a smaller and smaller focal length here. Right? And to get a smaller and smaller focal length, that's why your body is designed to change its focal length. And so what happens is this muscle is going to squish down. This is going to then make some curvature, and it's going to make the focal length just the right size. And so I can see something that's close that way because my body then can change the focal length. And of course, what happens with age is the ability for the lens to squish diminishes. And so as you get older, you have hard time seeing and reading things that are close, because to see things that are close, your lens has to be squishable. And your body loses that. And so most older people don't, see well close, and they have reading glasses for just that reason. And so I'm sure your days will come too, but enjoy it now that you probably don't need reading glasses. And these start to happen in the 40s and the 50s where you have to have the glasses. So, and that, like I said, that little squishy thing. Well, again, probably too much time here. I'll just jump to the telescope real quick too. But again, obviously there are many optical things around us, and again, we just kind of need to move on. But your author has some good pictures. I particularly like this one. This is just a simple lens, just the magnify. That's the one I put up in front. But if you were to look at an object that is close to a double convex lens, it will form a virtual image that is magnified. And the microscope takes advantage of that, and telescope, with a double lens system. This is probably a good model of that. Is because you put something fairly close to an objective lens. Maybe this is microscope slide. This would then make, if it's just outside of the focal point, would make a magnified image over here. It would be upside down and bigger. If you then took a second lens, then the image from the first one becomes the object for a second. And if you put the second one just inside the focal length of this one would then make a virtual, so it's far away from you and bigger. It's not inverted, although remember the first one inverted it, so this is not inverted from here, but this is inverted from that one. And so the overall effect of a microscope is it's inverted, which maybe you guys remember from your biology days or when your biology labs come. And every time I look at those microscopes, you always move it the wrong way. You're looking at it, you go, oh, I want to go to the right. And you move the slide to the right, and the image goes to the left. And this is why. It's because the objective piece flips everything backwards. But you get a double magnification, and that's what we talked about for the mirrors. That's what you'll do tomorrow in the lab. You'll actually build something very similar to this. We won't call it a microscope, but we will have the double lens system, and you will build it, and you will see that it is magnified here. The telescope, same idea. The only difference with the telescope is that the light that comes in from far away. And so that means that no matter what we do on this end of the telescope, we can pretty much say that our object is really far away. We can climb a mountain and go a couple thousand feet closer to the sun, but it's still 93 million miles away. So you really can't change that part of it. So there's a little difference between the telescope and the microscope, but like not much. But basically the idea of the first lens is to really take the light that's far away and make a real image of it so it gets inverted. So that then the second lens can be adjusted close and far, and we can change the magnification on the second lens by looking at how close and far we are to our, I'll call it the object of the eyepiece, but the object for the eyepiece is the image from the objective lens there. And so that's really the role of the first lens, is to get an image of whatever we're looking at. Maybe the moon last night, if anybody stayed up to watch the eclipse there. It was kind of a bust, huh? It was down. So between the fog and the lack of redness, it was just unimpressive, but oh well. I could say I saw it, I saw the eclipse. But anyways, that's the idea of the telescope. Bummer, I didn't want to quite take that much time either, but let's look now at some problems real quick. I got 3 that I thought might make a good set of problems to do involving the lens. You might remember we did a bunch from the mirror already, or maybe not a bunch, more like only 3. But let's take a look then. I got number 36 here as my first example. Actually, it's 26, but I'm going to jump to 36. Let's just do 2 here. I think 36 will answer what I want you to get out of 26 also. Let's, what'd I say, 36? Learning to drive this thing. We'll go to 100% there. Yeah, good. It has movement in it. Because I do want to do this example for what hopefully is the following reason. I haven't done any with a lens, but I hope what I did get across is that still works for the lens. And so just like we did the mirrors, I think we started off with that hubcap that was polished on both the inside and the outside, and the sports car enthusiast, we can do the same thing here. Now look at this. This one sounds like someone's trying to take a picture of an antelope here. We got an antelope. The distance is 20 meters away from a converging lens which has a focal length of 30. The lens forms an image of the animal. Now, if the antelope is running away, so you go take a picture, you spook it, it kind of runs away, which is probably better to run away than towards you, I guess. Running away from the lens at a speed of 5 meters per second, how fast is the image moving? Does the image move toward or away from the lens? Now, this is a question about motion, but before we even get to motion, let's just do distance here. Let's just take this and say, okay, here is 20 meters for the distance of the antelope. The focal length of this lens is 30 centimeters. So to keep my units matching, I will put 0.3 right there. When I go to calculate Q, and maybe you saw this in what we just said about the eye, you can hopefully see here that this distance, although it's 20 meters, I would not call 20 meters infinity. But 1 over 20 is significantly smaller than 1 over 0.3. And so it wouldn't surprise me if this could almost be just ignored, and that my image distance would be the focal length. I am looking at something far away. So let's see what I get. I've got 0.3 reciprocal minus 20 reciprocal, inner reciprocal of that, and I come up with a 0.304. Yeah. And so there is my image distance. If I was drawing it, I would have a focal length of here, but I have an object really far away. And so there's the image of the antelope. And like the camera one we just saw, it's inverted, and hopefully it's on my CCD array of my camera in focus so that I can then snap the picture and have the antelope. Pardon me?
Is that right?
I hope it's right. Did I?
Oh, never mind. Yeah.
And so it's almost at the focal point. So anything that's about 20 meters, we'll just say that, look, that's infinity. So everybody asks you what infinity is, you now know it. It's 20 meters. There it is. Okay? And you're going to do the same thing in lab tomorrow. You're going to take your optics and you are going to point it out the window like we did last time. You're going to focus it on something far away. Last time we did the cafeteria or the palm trees over at the bookstore. And those were more than 20 meters, but certainly probably around 40 to 50 meters. And we just said, look, it's infinitely far away. Not exactly, but close enough. So 20, 40, infinity, same thing, right? All right. And so that's what roughly happens with our mathematics. Now, that's not really the question here. That was really question 26, but to save time, I thought I would incorporate 26 with 36, because 36 is a little different. 36 says, well, now wait a minute. We have a moving object. So what does that mean about the image? It's moving also. And of course, then a camera needs to adjust for that if we want to keep it in focus. And so how or what is the speed of that image? Now in this case, they have it moving away from the camera. Okay. And as it moves further and further out, what happens to the image? Smaller and smaller, and gets closer and closer to the focal length, right? So as the antelope is moving away from the lens, the image is moving towards the lens. Fair enough? And this will take us back to physics 122. How do I get velocities out of this? Take the derivative, right? And so if I were to start with 1 over p plus 1 over q is equal to 1 over f, and I took the derivative of that equation with respect to time, what would I get? Well, I guess I'd get a negative 1 p squared dp dt, right? And so that's the derivative of p, 1 over p, with respect to time. Same thing with q. You'd get a negative, then you would add 1 or subtract 1 from the exponent, which gives you a negative 2, then you would get dq dt. And then you would have the focal length of the lens, but that is based upon the radius of curvature, which doesn't change. So derivative of a constant is 0. And then, as I go to kind of put this in here, I would have a 20 squared for the current position of the envelope. I've got the negative. What does dp dt mean? Yeah, that is the rate at which the object is changing. That's the what I call the real movement of the envelope. And so it is moving at 5 meters per second. Which way, though? Away. So is this a positive 5 or a negative 5? Is p getting bigger or smaller? It's getting bigger, right? So this is a positive 5 meters per second there. I'll move it to the other side of the equation because image distance I just did, 0.304 squared. And then I would have negative dq, I'm sorry, positive when I move to the other side, dq dt. And that's what we're after. What is the velocity of the image? And so I get what? Well, I get a 5 divided by 20 squared, and then multiply that by 0.304 squared, and I got some pretty small numbers here. Negative 0.001 meters per second. And I think that kind of makes sense, I guess, if you realize that we already had something pretty far away. It was already 20 meters away, which meant the focus point was almost already at the focal length. It was a little closer to that. And as the object moves further and further away, it's just going to get closer and closer to the focal length. But it's not going to change by much. The most it will change is by 4 millimeters if it ran all the way to infinity. So the envelope's got to go from 20 to infinity, and it's only going to change the image by 4 millimeters. And that's why, you know, my camera, truth is, when I focus on something 20 meters away, it's pretty well focused for something at 30 and 40 and 50 and 100 and 1,000. It just, the position of the image doesn't change much at that point. It's the things that are closer in that have a significant change. That's why in movies, you know, you'll see that. You'll have something at a distance, and everything at a distance is in focus. And then they'll focus close in, maybe on a table. And so the table's in focus, and the people at the table, but beyond them, at the distance, they're out of focus. And sometimes the artist, I think, does a good job of taking advantage of that. They change the focusing plane from the table, and it blurs out, and then the things at a distance come into focus. And I don't know, I always like that for some reason. But they do that in Lion King, which that one really bothers me, I guess, because it's an animation. It's a drawing. You could make it in focus near and far. But they keep that same thing as they move the lens in and out. Yeah.
Why does the 1 over f turn into 0 when you take the derivative?
It's constant.
But wouldn't it just still be 1 over f then?
No, derivative constant 0. I guess it's negative 1 over f squared df dt. And df dt is 0. Yeah, so 0. Well, I'll try one more and we better get out of here. But here's the grand finale here. Number, I think it was 64. 64 is a good one. It is a magenta. And it's got a lens and it's got a mirror. And it does the radius of curvature, and so it's got all of our wonderful pieces in here. So let's see if we can do this, and then we'll move on to the next chapter. But putting this one together here doesn't have any motion, so no derivatives, but let's read this one together. It says here that this figure down here, figure 64, shows a thin converging lens which has a radius of curvature R1 of 9 and R2 of negative 11. The lens is in front of a concave spherical mirror of radius 8. A. Assuming the focal points F1 and F2 are 5 centimeters from the center of the lens, determine the index of refraction. So the point of this first one is really back here. Back to what you sometimes refer to as the lens maker equation. If you want to make a lens, if you want the lens to have a focal length of 5, which is what we want here, and I'll do it in units of centimeters. And so this one says I want to have a focal length of 5 centimeters. Then, as I build this lens, I have some options here. I can choose different radius of curvatures. I could have one inside flat. I could do different indices of what the glass is made out of. It's kind of my choice there. If I take a small indices, I probably have to have more curvature to it. Or I could have less curvature if I'm willing to go with a high index, which in my case, this is what my glasses are. They're what they call a high index material. And then that way you don't have to curve them as much. And if you don't have to curve them as much, then you don't have to make them as thick and as heavy. So you pay an extra premium for that. But that's, kind of your choice here. And so our choice here is that we want to know what the index needs to be. We are the lens maker here. We want to ask that question. A, assuming, determine the index of refraction. So they give us the radius of curvatures. So this becomes a 1 over, and R1 was it 9 up there? 9. And the other one, they said, is a negative 11. Again, all my units are in centimeters, 9 and 11. Now, let's look closely. They gave me a picture, but you can see that if the light is coming into this side, wouldn't that be a positive? But the other one would be a negative. So that's good. That's the order they gave me, a positive 9 and a negative 11. So I obviously have a little bit of calculator work to do before I can get my index of refraction here. Maybe I'll start with this number, 9 reciprocal plus 11 reciprocal, and put that together so I have a number. Let me come over here. This is 1/5. I'll just write that as 0.2 divided by that last answer I got. And I got 0.99. And so 1.99 would be the required value for this material in order for it to have that focal length and those radius of curvatures, which seems like a high index, pretty high. So it's either got to be fancy material or we better change our radius here. Something different to get that focal length. Huh? Pardon me?
Cubic zirconium glasses.
Oh, yeah. So there's my end. Now that's one of many reasons I wanted to approach this one, but let's go on to B. B then says the lens and the mirror are 20 centimeters apart, and an object is 8 centimeters to the left of the lens. Determine the position of the final image and the magnification as seen by the eye in the figure. And then C, is this final image inverted or upright? Please explain. So I would start off by saying, okay, here is what I have so far. I'll just forget the mirror for a moment. But I would start off with this lens and say, okay, here is a focal length of 5 and an object distance, I believe I read 8. Is that true? No. That was radius of curvature. Oh no, that's 8 also. They're both 8. Okay. So an object is placed 8 centimeters to the left. Now if I was drawing a ray diagram, it would look like that. And I know this doesn't really go through the lens, but remember the light that does go through the lens does the same thing. So there's where the image would be formed. Remember, we said this is like the concave mirror. So if you are between the focal point and twice the focal point, which I am, we should create a real upside down, larger image. And that's what my picture is showing. I can calculate it. I can say 1 over P plus 1 over Q equals to 1 over F. My P is 1 over 8. My Q is I would like to find. My focal length is 5. And so grabbing my calculator, I will go 5 reciprocal minus 8 reciprocal, enter. Take the reciprocal of that, and we're looking at a distance of 13.3 centimeters. So maybe I drew it disproportionately too far out there. I think I drew it a little too disproportionately close. Because if that's 5, 8 would probably be more like here. But nonetheless, without me doing it again, I'm hoping you will see that that is the image. Because then there is a mirror. Now they said the mirror was 20 centimeters away from the lens. So let's apply the 1 over P plus the 1 over Q equaling the 1 over F to the mirror now. Because with, again, a multiple optical system, the image created from the first one becomes the object for the second one, as we tried to explain. And this problem illustrates it well. It illustrates some other things really well too, but we'll keep showing those as we go along here. But here I need a P. Well, if this distance here is 13.3, then when I subtract 7, or 20, I get 6.67. Is it a positive or a negative P? Yeah, it's positive, right? And so the image is formed right here before the light gets to the mirror. Remember the negative P, which isn't showing up in this problem, but it did on the one, would be the image would have to be formed back here. So this is a positive distance. I'd like to find the Q, where is the image from the mirror, and my F is the focal length of the mirror, which they didn't give directly, but what did they say? The radius of curvature is 8. So it's half that. So this is a 1 over 4. And so the focal length is about here, and twice the focal length is about there. And again, for this mirror then, we should form a reflection and a real image outside of the radius of curvature. And so 4 reciprocal minus 6.67 reciprocal, and the reciprocal of that is roughly 10. And so we're looking at 10 centimeters. Maybe I'll change colors to kind of draw what would happen here. But this ray that is coming from there, which of course originally came from here, would then bounce off and go through that focal point. A second ray that comes from here, going through that focal point, would bounce off and go parallel. And so there is the image formed, or what I'll call the second image. which we've just calculated is 10 centimeters away from the mirror. And so notice I've drawn the ray coming from this. Now, I did not trace it back to here. I guess if it actually existed, this would have been the ray that came out to here, hit this big lens, bent, and did that. Now, unless the lens is really big, that ray doesn't really exist. But don't get me wrong, I could draw it, because what I do know is the rays that do go here, then converge here, then spread out here, and then converge there. So that's the group of rays that probably really exist. Those are the ones that can only go through here, group to here, spread out, ricochet off, and regroup to there. But the other rays are just a way of mathematically saying those are the ones I know about. Those are the ones I can draw. Those are the ones you're going to need to do on the lab tomorrow when you start drawing these and calculating them and figuring out where the image is. But we're not done, because what happens next? Doesn't the light come back through this lens? And so this person over here viewing, and I'm sure this is why the author made it magenta and actually put these words, determine the position of the final image, not the third image, the final image, and its magnification is seen by the eye in the figure. And so there is yet a third image as we bounce off. Maybe I'll draw that in green here. And so again, if these are the focal points, a green ray would hit this lens and bounce off and go that way. This one would come here and hit that lens and go parallel. And my third image then in green would be right there. And then to calculate that third one, I would have to write out 1 over P plus 1 over Q equals 1 over F. And in this case, what is my object distance? Yeah, not shown well in my figure, but if we're 10 from here, and the whole thing was 20, then this must be 10. What's my focal length? The light's going the other direction though. Is it still 5? Right, and that was our discussion an hour ago. You still get the same focal length here. And so this will give me my Q and the position of my final image. So 5 reciprocal minus 10 reciprocal, enter reciprocal of all that, ends up with a 10. And so to answer part of their question, where is the final image? It is 10 centimeters to the left of the lens. And so it's almost at the same place as the original object. It is upside down, right? It was inverted here, inverted yet again, and inverted yet again. And so this person over here is going to see an inverted image. And it's going to see the original object, if you will. Of course, it won't see all these. These lights never went to the person's eyes. These were just part of the process of getting that one. And so as I look at the magnification, I would have the magnification the first time. The first time was back here, where we had a negative 13.3 for the image, no, positive, oh, yeah. It's negative image distance, and so negative of 13.3. We started at a distance of 8. And so 13.3 divided by 8 is about 1.66 negative. And so as my drawing hopefully indicates, it is upside down and a little bit bigger. The next magnification, magnification number 2, is what happens into the mirror. In the mirror, we have a negative. We had an object distance of 10. We had an image distance of 6 2/3. And so if I go 10 and divide it by 6 2/3, I get about a 1.5 negative. And so now it is bigger and inverted yet again. That's why it's right side up after that second magnification. And then finally, the third time, the final image is at 10. I think it started at 10 too, right? Started at 10. So that's just a -1. And so the last part of this lens just kind of inverted. It didn't make it bigger or smaller. So the total magnification and the total size is all three of them put together there. So 1.66 times 1.5 times 1 and times negative, negative, and negative make a -2.5. And so when it's all said and done, it is bigger by 2.5 times, and it is upside down. Yeah.
Why is it not just the last one?
This magnification means, the last one, means how much bigger is this one compared to this one. And this one is already bigger than that. And then this one's bigger than that one. And so right, we have, double, 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 or whatever the case may be. Yes?
Can you go over how we determine whether or not P is positive or negative for the lens?
Now, whether it's the lens, P, right? Whether it's the lens or the mirror, okay? The only way to get a negative is if you have the lens or mirror in a position before the image is created. Here's what I mean by that. Maybe orange might look good here. If I were to start here and realize that this is where the image is formed, anything placed on this side would give me a positive P. Anything placed this side would give me a negative P. So if I had put a lens right there, and let's just say that was 10 centimeters away, then this distance would be 3.3. And in my equation, I would put in 3.3, but I'd put a negative 3.3. Why a negative? Because it's what we call a virtual object. If you put the lens or the mirror before the image is actually created, then you get a negative P. So in our case, we put the mirror over here. And it wouldn't matter if we put a mirror or a lens here, it is still a positive P because the image was formed first, then the light went to it. But if it hits this first, it hasn't really been formed yet, and that's why we call it virtual, and that's how we treat it with a negative.
So then it seems like if we were to have an actual object, it would always be positive?
Yeah, so you can only get a negative P when you have a multiple mirror or lens system. Okay. Yes, definitely. Because for the first one, right, it has to be a virtual object. So you could never have it for the first one, because the object will always be real the first time. It's later on that it becomes negative. Good, and I'm glad you understand, because again, you're going to be asked to do this tomorrow in the lab, and that confuses some students, because what they do is they take the object, they take the lens, they form the image, and then they put another lens right here. Then the instructions say, form a virtual object. Like, what? And basically what it means is put the lens here. Put the lens someplace before the image was formed. Yeah. Well, with all that said, let me do what we can to get out of this chapter. and still be in optics, but switch gears a little bit, because as you saw, there is a lot we can do with geometric optics, and a lot we have been doing. We don't have enough time to do it justice. I think we've done a pretty good job of what little time we did and what time we stole from what will be other topics there. But let's continue to look at our optics, but let's change our viewpoint, if you will. Don't think I'll need this anymore. But here's what I mean by this. Our optics can be divided really into two categories. I would say what we've done so far, Chapter 35 and Chapter 36, I would classify as ray optics. We learned about why light reflects and refracts and how you calculate the new angle. We called that Snell's law, or the law of reflection. Okay. Then we applied it to our mirrors and our lenses and got kind of carried away with how many examples and discussions we had with it. But what we haven't done in any of our optics, which you are going to see now in Chapter 37 and Chapter 38, at least what little we're going to be able to do in Chapter 38 before we better change topics and go on to modern physics, is we have not been treating our optics as waves. We have not discussed about their wavelength, their frequency, and, very important, the interference between them. And so part of what we need to remember for this next two chapters to make sense, remember all that good wave stuff we did with sound waves? Remember the constructive and destructive interference, the phase shift on reflection, all those wonderful things? We're going to see them all again. We're also going to see them in the modern physics. And so we need to talk about our waves again. And in fact, this chapter 37 can be classified real simply as we are going to look at a couple of examples of where you have interference. We are going to look at the superpositioning of light waves as we come together. That would summarize it really well. Whereas 38, we're going to look at something called diffraction. And if we have time, and hopefully we'll have just a little bit of time to mention it, we will do some polarization. And it's probably worth mentioning what is diffraction. That's probably a new word for you. Maybe polarization is too, but diffraction, I'm going to need you to kind of get a rough idea of diffraction before we get into Chapter 38. And so I'm going to say diffraction is the spreading of the waves. Because I want to show you something that I don't really want to use diffraction yet. I don't want to explain why there is diffraction. Again, we'll talk about that in 38. But to start 37, I want you to see something, and this is why I set this experiment up here. I have a very tiny opening there. In fact, it might be so small, I don't know if you can even see light behind it. But there is, I should have brought a flashlight or something there to see, but it's a very small opening. And it's adjustable, and so I'll play with it. In fact, I'll just open it real big right now. So that, I know you can see. That is a big opening. And if I were to take a laser beam, so I will turn on the laser here. I will shine it on the screen over here, and so I have a red dot. And so I am sending light of wavelength about 632 nanometers. Okay? And so there it goes through the air. If I send it through this little opening, probably not too much of a surprise. It's a big opening. It goes right through it and shows up there, right? But what I do want you to see is, what if I make the opening small? I'm not sure I'd call that small yet. I'm hoping it's big enough that you can probably see that it's still open. What if I were to shine the light through that now? And maybe you can just begin to see the effects. Do you see anything there? it is hopefully beginning to spread. That's the word diffraction. Now, why it spreads, like I said, we'll get more on that when we get to chapter 38. But I just wanted to show you first that there is diffraction, because I'm going to take advantage of diffraction to show you some other things before we even get to diffraction. But you have to understand that there is diffraction in for the what's coming next to make sense. I'll tighten it up a little bit. Let me make the hole, let me get a little bit of light through it, even smaller. Ooh, there's a smaller opening. And tell me what you see. Does it look like it's spread out? Yeah. And I could even squeeze it a little bit more. Right. There we go. Squeeze it. And it oh, there we go. Squeeze. Oh, there we go. Now obviously it gets a little dimmer since less light's getting through. But it's also spreading out. Fair enough? So you can imagine if I made this infinitely small, wouldn't it spread out equally in all directions? Now you'll notice that it doesn't really spread equally in all directions. It just kind of spreads this much. Fair enough? But the smaller I make it, see how it was spreading out more and more and more? So the diffraction itself is a pretty complicated topic. So that's why we are going to wait till next chapter to completely talk about diffraction. What I want to do here, in what little time we have left, is to say, what would happen if I did this? What if I were to start with my laser beam and shine it through not just a single slit, but a double slit. And so this experiment, made by the greatest scientist of all times, the Young's double slit experiment. I've always wondered if there's some kind of relation, but since I am what I call a true American, meaning my family immigrated from who knows when, from who knows where, and who knows from what reasons. Farthest I can figure out is they came from Pennsylvania. With a lot of tragedy along the way. They tried to farm in Nebraska, that didn't work. They went to Colorado, that didn't work. They ended up in poverty. Finally got something going in Idaho. Until their stove blew up and killed all their children. So eventually, some great-grandfather of mine decided that they would give up farming. They were never good farmers. They lost everything all the time. And one child fell in the fire during the pilgrimage to Colorado. So that's about as much as I know. So, but I do know this, that they were terrible farmers. And every time my great something plowed the field, his neighbor would say, "Your lines are crooked." He goes, "You know, you're right." And so he'd plow it again. And he plowed again and again and again and again. And he always missed the planting season. Finally, somebody said, "You know, you can plant on a crooked row." "Really?" "No." So I told him, "You ought to be an engineer." Because you keep doing it to this minute detail, you are going to starve to death. So during the Great Depression, they left Idaho, ended up San Jose State, and became an engineer. My father, and then me, and then so they never actually finished school because they didn't have enough money. So finally, I did. There's my life story right there. So finally, but that was a big deal. Actually, it was my uncle finished first. So because my mom, that's my mom's side of my family, and in those days, you know, women weren't allowed to be engineers, so she didn't go to school, but they highly encouraged my uncle. But anyways, more to the story later. All right, but there is the Young's double slit. So like I said, and that's how I got started on there. I always kind of wonder if there's some kind of relationship, but I guess I will never know. But same part of the European continent. But what would happen here? What would happen if the light shined through this hole? Well, let me draw this. This is the part I was trying to illustrate with this simple experiment. That when it goes through a hole, it will spread out. Again, not going into the details of why it spreads out yet, that's coming up, but it will spread out. That's the key, because what would happen in the other hole? It too would spread out. So if over here, a distance L away, you put a screen, what would you see at, say, point P on the screen, now that we have shined the light through two holes? And maybe I'll change colors here. Maybe I'll go to red since I'm actually shining a red laser. Wouldn't the light from this bottom hole go to the point P, but also from the top? And so what we get is we get two waves of light hitting that point. This is where the wave part comes in. How do you add two waves together? Superpositioning, right? And if the two crests line up, then they double, right? And that's going to be the light adding together. That's going to be constructive interference. It's going to be really bright. But what if a crest lines up with a trough from the other wave? They cancel. And so what would we call canceling? Destructive, dark, no light, gone. And so what I should have is, as I go from the center, which I will call y equals to 0, and I move out, there should be patterns where sometimes the light adds up together constructively and sometimes it adds up destructively. Let's talk a little bit more about that. My picture's getting kind of busy, so I'll do it again. Here is the double slit. Here is the screen. Let's talk about straight down the center here. How would the light from the bottom slit compare to the light from the top slit? Wouldn't they be the same distance? And I don't know what that distance is. I do know that the wavelength of light is only 632 nanometers. Even if I round that to 1,000 and call it 1 micron, that means I have 1,000 wavelengths in 1 meter. So there's probably 1,000 wavelengths here, another 1,000 here, and another 1,000 here. So there's 3,000 little wavelengths, but I do know this, that whether it be 3,000 or 300,000, I know that the number here and the number here are the same. So how do these two match up? Right, in phase, constructive. At one moment in time, there would be a crest, and it would match with a crest. Another moment in time would be a trough, but it would match with a trough. And so crests would line with crests, troughs would line with troughs, and I would think then that I would have constructive interference. I would have what I would call a bright spot. I would call what I have a maximum interference pattern right down the center. However, what might happen as I move off of center? And in this case, either down or up. What's going to happen? At some point, maybe I'll change colors here, you will hopefully see that the blue one travels a greater distance. The top one blue, travels a greater distance than the bottom one blue. And what if that greater distance is a half a wavelength? What would happen? They would cancel. And so instead of being bright, I would get dark. Instead of calling it maximum interference, I would call it minimum interference. Because one does travel a little bit further. I'll label it as a delta. Delta is this path difference. How much more does one travel compared to the other? Remember doing this for sound waves? And so we're going to do the same thing. We're just doing it now for light waves. And I'll give you a little hint. everything we do for this entire chapter, although we do many different cases, it's all going to be based on this interference. It's all going to be based upon take two rays, put them together, see how they come together. Are they constructive? Are they destructive? Are they something in between? And so I will have a path difference. And in this case, it would be a half wavelength. I'll try it again. What would happen perhaps a little further down? I'll represent the two waves here in green for a second. But if I go far enough down, it is quite possible that the light coming from the top hole travels a whole wavelength further than the light from the bottom hole. What happens then? They are back to constructive. Crests line up with crests. And so instead of having, how many wavelengths did we say here roughly? Was a micron. So, yeah, so it was roughly a 3,000. Okay. Wait, micron. 1,000? 3? I'm sorry, I said it wrong. Micron, it's a million. Yeah. So, a million. So it's basically a million in 1 meter. So I have 3 million wavelengths here. Actually more than that, because this isn't quite 1 micron. But again, just kind of rounding it. I want you to realize it is not so much how many waves I have. What's important is the difference between them. And so this one may have my 3 million wavelengths, but this has 3,000,001. It's a little bit more. And if it's a little bit more, then crests line up with crests, and troughs line up with troughs, and we get constructive interference. And in this case, the path difference would be 1 wavelength. I'm hoping you can see this game would continue. A little further down, it would be dark. I would call that a minimum spot. Here, the path length would be, 1.5 wavelengths. A little bit further down, it would become bright again. I would call that a maximum because the path difference is 2 wavelengths. And simply put, I would get a bright spot every time there is an integer number of waves between those two openings. And I would get a dark spot anytime it was an integer and a half.
Which one is dark and mid? Is it the top? I mean, both the top and the bottom, the upper, like upper half. That's also dark and mid, right? So is that there also?
Okay, so if I say this right, please notice what I've done is just one direction. Doesn't the same thing happen in the other direction? And maybe I shouldn't have put this. We don't usually label things by their dark one, because I think that's your question. What I would then label them is I would say here m equals 0. The center one would be labeled 0. The next bright one down here would be m equal 1. The path difference is 1 wavelength. The bright one down here would be labeled as 2. Just to include direction, I would have another bright one up here. I would label it as m equal -1. And m equal -2, and m equal -3, if you wanted to keep pluses and minus. But again, this first step here is really the foundation for the rest of the chapter. Do you see how we're just going to do interference? Do you see the key to interference is looking at the path difference between them? Now we're going to do a lot more than just that, and the geometry will become a little bit harder. But let me give it a shot here. I will remove this single slit, and I will replace it with, and again, too close for you to see, but when you get your chance to do this in lab, right here, what it calls a number 2, has 2 very thin narrow strips, and I'm going to shine the light through there. They're small, which unfortunately means you can't see them from your distance. But the whole idea that they are small means the light would diffract out. And I need them to go onto the entire screen from each hole so that I can get this interference pattern. And so, if I take the laser beam and I shine it through the hole, maybe I'll turn down the lights here. If I can find the little opening here in the dark, you will see a pattern of bright, dark, bright, dark, bright, dark, bright, dark. Now notice there is a fading effect also. That is caused by, remember how I said it spreads out and I just kind of assumed it spread evenly? Did it really when you saw the experiment? Wasn't it more concentrated down the center and less spreading out there? So again, more on this when we get to chapter 38. We'll come back to this, but forgetting the fact that it's more intense here and a little less intense over there, at least this gives us a place to start, that it'll go bright, dark, bright, dark, bright, dark. And in fact, I think my other setting is a little clearer. And maybe you can see them a little bit better. It looks like you can even see them with the lights on, but the lights off, I think you can see bright, dark, bright, dark, bright, dark, bright, dark a little bit better. Now, where would these bright spots be? Now that we kind of understand the physics that you must get bright spot when they're one wavelength apart, shouldn't we be able to calculate where they are? And so let's do a little geometry here. Let's take and say, all right, here is the double slit. I'll go ahead and draw one ray there and one ray there. And as I was trying to argue here, that they will get bright when you're an integer number of wavelengths. Different. Because as I was saying, I don't really care how many total waves there are. What I care about is how many more waves are in the top one compared to the bottom one. So what I'm going to do is draw a line across here and say from here to the screen and here to the screen are the same. So that right there is the delta. That is where the path difference is. Because even though the total length to the screen is about 3 meters, since one is just a fraction more than the other, one is only 1 micron further than the other. That small distance can all be explained right there. Let's do this. Let's call D the distance between the two holes, the two slits. Let's also do this. I'll change colors to help here. But if I were to draw straight down the center, which remember, so we said straight down the center would be the bright spot. And as you pointed out, Lester, there wouldn't be equal intensity. So the center one is easy to pick out. It is the brightest one down all of those. And so there's the bright one. But if I look off the screen by an angle of theta, okay? So again, if I was back over here and I'm looking at the light coming right at me, and then I move down the screen so that there's an angle theta. That angle theta, if we do a little geometry, is going to be the same. Let me finish the triangle here. that would also be theta. Because that in there is theta. That would be the complement of theta. And that would be the complement of theta. And so we're back to that little tiny angle as theta. And so let's take a look at this right triangle I have right there. Isn't the path difference, the delta, opposite of the angle theta? And D is the hypotenuse? So, from my trigonometry, isn't that the path difference? So the path difference is dependent, and it kind of makes sense, on what is the distance between the two slits, which I think this one labeled 1/10 of a millimeter between the two slits, okay? And then what angle do you have? That's the path difference. If that path difference, if delta, which is d sine theta, equals an integer number of an integer number of wavelengths, what are you going to get? That's where you get the bright spot. And if that made sense to you, all these crazy things we're about to do next are going to be a piece of cake, because it's path difference and whether they come together and you get constructive or destructive interference.
Is that angle really a right angle?
Not exactly. Okay, fair enough. If you want to real press me on this, but just like we did for the optics, those can't be right angles because they would never meet. So they have to be near right angles. And that's why you can see in the experiment, I have my slits close together and my screen far apart. So that's 3 meters, and that's 1/10 of a millimeter. And so, you know, we've got over 10,000 ratio between the size of the D. And so those angles are not exactly right angles, but they're probably 89.999 degrees. So again, this is a small angle approximation. And so our first equation for this chapter is this. This is where you will get bright spots. And you will get the dark spots halfway in between. If we add one more piece of geometry, we may want to put it not in terms of the angle. Because the truth is, when I start measuring these, and I go, okay, here's a bright spot, here's a bright spot, here's a bright spot, here's a bright spot, I'm probably going to be measuring along the screen a distance. I'm not going to be coming over here with a protractor and measuring angle. So although this is true, it probably is a little bit better to make the next step and say, if I write the tangents of theta, the tangent of theta would be the distance along the screen. Let me call it y. And then L is the distance to the screen. And so that's a y over L. And as you pointed out, we're doing small angles. So small angles, sine theta is pretty close to theta, which is pretty close to tangent theta. So I'm going to make a substitution right here. I know it says sine here, and it says tangent there, but for small angles, they are pretty much the same. So again, if you're willing to say, let's not talk about more than 30 degrees, then they are pretty much the same in radians. So I can put dy over L equals m lambda. If I solve it for y, then the location where there are bright spots would be this. And so both of these equations will serve us well. The first one is kind of the basic, but it is in terms of the angle. So when we get into the lab, we probably are going to measure more things in y. And of course, the distance to the screen and the distance between the slits. So let's talk a little bit about this. How much time do we have here? Maybe just a few moments, and let's make some modifications here. For example, what would happen if instead of having a red laser, I had a blue laser? What would I see on the screen? So if I take a red laser and I shine it through my double slit, and I put a screen over here, where does the red light show up? How about right down the center? What happens down the center? Bright spot, right? I'll make like a little hump here saying, okay, there's bright light. Will I get other places where there's bright light? Oh, absolutely, right? That's what this red laser beam is doing. It's saying there's a whole series of bright, dark, bright, dark. We call that fringes. And so there's a fringe pattern. We would come down here, and someplace over here, I would have m equal to 1. This would be m equal to 0. The math I just did would fit right in here. If I wanted to find how far down the screen I'd have to go, I'd set m equal to 1. I would need the wavelength, and this happens to be 632 nanometers. I need to know the length to the screen, which in this case is about 3 meters. And I need to know the separational distance, which in this case is about 1/10 of a millimeter. But I could calculate where the next bright red one would. And wouldn't there be another one down here? And same thing up above? But if at the same time, or just change it up with a blue laser, what would I get by shining a blue laser through here? What would happen down the center? I'd get bright blue there. In fact, wouldn't I always get a bright spot down the center no matter what the wavelength is? Yeah. And so in this case, a red and a blue, they'd both overlap. I would call it magenta. And so I'd get kind of a magenta color down the center. But would I also get a fringe pattern in the blue? Yeah, and what would it look like here on the screen? Would the bright spots for the blue one be at the same place as the red ones? No. Why? Yeah, the wavelength is different. And so the blue ones would show up maybe, say, here. And so when we start talking about m equal 1 and m equal -1, we also got to say what color are we talking about if we have more than one wavelength going through our double slit. And we would also have an m equal 2. Maybe it would fit right about here. M equal 2. M equal 2. And so notice the blue having a shorter wavelength means that it would show up at y, smaller values, and the angle would be at smaller values. Last question, and then we'll go then. So what if this was white light? So down the center, all the colors would interfere. What would you see down the center? White. What would you see here? You'd see a rainbow. Everything from violet at the shortest to red at the longest. And then you would see a rainbow again. Violet to red, and then violet to red. And actually, they might start overlapping here in order 3, which they will overlap in order 3, as you will see real soon when we do this in lab with our double slits. But that'll be our stopping point for today.